Today's lesson is the first of 4 different calculations that I will be teaching you that I like to call the basic gas law calculations. And by basic gas law calculations, I am referring to Boyle's Law, Charles' Law, Gay-Lussac's Law, and the combined gas law. And what all of these gas laws have in common is that they deal with 3 variables. We are going to be looking at volume, pressure, and temperature for a gas, and we're going to look at how those 3 things interact together to tell us about the characteristics of a gas at a specified temperature, pressure, and or volume. So real quickly, before we actually begin the first calculation, I want to go over some basics. So when we're dealing with gas laws, the ones that I'm going to be talking about today, volume, the symbol is V. Most of you already know that. And most commonly, you're going to see volume measured in milliliters or liters. But keep in mind, you could really use any volume, but that's primarily what you will see. Pressure, the symbol is P, and pressure can be measured in a variety of ways. Some of these you've probably seen before, some might be new. Atmospheres, that's ATM, kilopascals, millimeter mercury, and torr. And for the problems that we'll be doing in the next 4 videos, you'll probably see a variety of these. They're very easy to work with. And the last one is temperature. T, uppercase T, is our symbol for temperature. And we normally measure temperature in Celsius or Fahrenheit, just kind of in everyday life. In science, especially in chemistry, you will often see Kelvin, Kelvin. Now, that might be a new unit for some of you. It's real easy to work with. As a matter of fact, I know a lot of students do not like converting back and forth between Celsius and Fahrenheit because you've got that 5/9 and 9/5 and it gets a little involved. The Celsius Kelvin conversion is super easy. All you do, if you want to know the Kelvin temperature of anything, is you just take the Celsius temperature and you add 273. Super easy. Also, you'll notice Kelvin does not have a degree sign like Celsius does. It's just capital K for Kelvin. So I've done 2 quick examples for you just to show you how to convert. For example, if you had 25 degrees Celsius and you wanted to convert that to Kelvin, you would just say 25 plus 273, which gives you 298. Or if you had 50 degrees Celsius and you wanted to convert that to Kelvin, you would just say 50 degrees Celsius plus 273, and that gives you 323K. So you'll have to do that quite a bit in these particular calculations because volume doesn't really matter. The unit of volume can be about anything for these. Pressure doesn't really matter. But for temperature, when you are plugging a temperature value into one of these basic gas laws, it specifically must be in Kelvin. And we'll have another lesson that goes into the reasons behind that, why it has to be that way. But for today, just learning Boyle's Law, you need to know that temperature must be plugged in as a Kelvin temperature. Even if they give you Celsius and they ask you for the answer in Celsius, you have to plug it into the problem as Kelvin and then convert it back at the end. Think about it as a key and a lock. So just something to keep in mind, and when we run into that in the problems, we'll definitely talk about it in a little bit more detail. So just make sure you know the 3 things you're going to see today are volume, pressure, and temperature. Now, something that I really like about gas law problems is they make sense. Most of us, we know what gases are. We use gases in our everyday life. You have air in your tires. You have aerosol cans. You know that aerosol cans are pressurized. You know what a helium tank is. You know what an oxygen tank is. So most of you have some firsthand experience with gases in some way, shape, or form. And when you're doing the problems, you can actually look at the information you're given, the answer that you get, and you can ask yourself, does that answer make sense? And we'll do that as we go through these. So the first law that we will look at in today's tutorial, and this is actually the only law I'm going to do in this tutorial. I've divided this up into 4 different videos. This first one is Boyle's Law. So Boyle's Law will be our first basic gas law. So let's see what Boyle's Law was all about. This law states that the volume and pressure of a sample of gas are inversely proportional. What that means is when one goes up, the other goes down. Now notice, here's a little disclaimer. They are inversely proportional to each other at constant temperature. So temperature does not change when we are doing a Boyle's Law calculation. Now what Boyle found out was that gases compress a lot like a spring. And when you put pressure, let's say you have a spring between your hands. If you put pressure on that spring, the pressure is increasing, but the volume is decreasing. But if you let that spring go, if you release that pressure, the spring is going to bounce back out and the volume is going to increase. So by springing back, he meant that the volume increases when the pressure is lowered. Now again, this is only true if temperature does not change, so temperature is constant. So we're going to make a couple little notes about Boyle's Law right here, and then we'll jump into the first example problem. It's really very easy. So the first thing that I would make a note of is that for Boyle's Law, when pressure goes up, volume goes down. Or likewise, you could say when pressure goes down, volume goes up. Also, I would make a note that this is only true when temperature is constant. So that is your general information. Now, the actual formula for Boyle's Law looks like this. P1 V1 equals P2 V2. Pressure 1 times volume 1 equals pressure 2 times volume 2. And you can see there's not a lot to this equation, so it's actually very easy to use. Now, what I encourage students to do is just to read the problem, label everything they know as either V1, P1, V2, or P2, rearrange the equation, and plug in. I like to go through the steps in that order because I think it makes it a lot easier, but I do want to tell you that's not the only way to do it. Some kids just like to plug everything in like this and then rearrange the numbers. I personally think it's easier to rearrange the equation and then put the numbers exactly where they go, but you know your math skills, so you do what works for you. So let's read this question. A sample of gas collected occupies a volume of 725 milliliters at a pressure of 1.4 atmospheres. What will the pressure be if the volume is decreased to 500 milliliters? So I can see here that it looks like they've given me a volume and a pressure and then another volume. They don't mention temperature anywhere. That is my cue to assume temperature is constant. If they either tell you it's constant or they just don't mention it, you assume temperature is constant. So the only thing I'm dealing with here are pressures and volumes, and that is my big clue that I am using Boyle's Law. Now, what I like to do is find the two that go together and make those my ones. And what I mean by that is, do you see how it's 725 milliliters at a pressure of 1.4 atmospheres? It's this many milliliters at this pressure. These two guys go together. So I'm going to make this my V1 and my P1. And then whatever is left over has to be the 2's. So since this is a volume, this would be V2, and it looks like they are asking me to solve for pressure, so that would be P2. So find the things that go together, make those your 1's, everything that's left are your 2's. That just makes reading through the word problem a little bit easier. So we know we have a Boyle's Law problem, so let's write the formula. It is P1 V1 equals P2 V2. Now, most students at this level are very comfortable with rearranging equations. Occasionally, I'll run into a student, maybe math is not their cup of tea, and they need just a little more help with it. It's fine. We can make this easy. We are solving for P2. So what I tell those students to do is circle what you're solving for. Your goal is to isolate that. You need to get P2 all by itself. How do we do that? We divide both sides by V2. The V2s here cancel. So what you have is P2 equals P1 times V1 over V2. Now, I'm really OCD. I like my unknown on the left, so I'm just going to rewrite that and flip sides. So P2 equals V1, P1, P1, V1, doesn't matter what order you put it in. I switched it over V2. The order of these doesn't matter. You're just multiplying those on top. So this is the formula I am plugging into. You don't have to flip it around and rewrite it. That might be a little overkill, but again, I like seeing my unknown on the left and everything I'm plugging into on the right. Now, the great thing about this is you have everything set up. Once you put the right numbers in these spots, all you're going to have to do is multiply and divide because you've already rearranged the formula. And even better than that, you've already marked everything up here. So it's just like you're picking it up and you're putting it where it goes, which makes your life so much easier. So let's plug in and figure out what our new pressure is. So pressure 2 equals volume 1, which we labeled as 725 milliliters. Now you want to make sure you put your units in the problem because then you can see everything cancel. P1 is right here, 1.40 atmospheres divided by volume 2, which I have labeled as 500 milliliters. See, because you labeled it early, now you don't have to worry about going back and finding it. You just pull it down and plug it in. Now, milliliters cancel, leaving me with atmospheres. That's good news because they have asked me to solve for pressure, and I know that atmospheres is a unit of pressure. So all I have to do is multiply 725 by 1.4 atmospheres equals divided by 500, and my new pressure is 2.03 atmospheres. Now, let's ask ourselves if that makes sense. So I started off with 725 milliliters of this gas at a pressure of 1.4. So let's say I had this much volume. Well, they're telling me the volume decreased. If the volume decreased, then that means pressure must be increasing because it's pushing everything together. So I would expect my final pressure to be higher than 1.4, and it is. It went up to 2.03. That makes sense. The correct units canceled, so if I was careful with the details, then my work should be correct. We're going to do one more example of Boyle's Law for this video. So let's take a look at the next one. We're going to do the exact same process that we just did. So a sample of nitrogen gas collected in the lab occupies a volume of 725 milliliters at a pressure of 0.971 atmospheres. So I know I've got a volume and a pressure, and those go together. That at's kind of a little key word for me right there. What volume will the gas occupy at a pressure of 1.4 atmospheres, assuming the temperature is constant? So they just told me temperature is constant. I'm only working with pressures and volumes, so I know I'm using Boyle's Law. The first thing I'm going to do is label everything. Because I'm starting with a gas at 725 milliliters at this pressure, this is my V1 and my P1. That means this outlier right here, this 1.4 atmospheres, I know that's a measure of pressure, must be my P2, and it looks like I am solving for V2. V2 is the one I don't know. So I'm going to write down my formula for Boyle's Law, and that is P1 V1 equals P2 V2. pressure 1 times volume 1 equals pressure 2 times volume 2. Now, it looks like I'm solving for the second volume. I'm going to circle that. How do I get V2 by itself? I divide both sides by P2. And again, I get that a lot of you watching this video could just do this little piece of math right in your head. That is fantastic, but if you need to break it down, it's really easy. Now again, you know I like flipping it around so that I'm looking at everything on one line. So, or my unknown on the left and my what I'm solving for on the right, I should say. So V2 equals P1 V1 over P2. You got to be really careful and pay attention to the details there because it's super easy to mix up all those ones and twos. If I'm not careful, I'll make a mistake real quick on this. Now, I'm ready to plug in. I've already got everything labeled from up here at the top, so let's do that. So V2 equals P1, which was 0.971 atmospheres, times V1, which was 725 milliliters, over P2, which was 1.4 atmospheres. Now, this time our atmospheres cancel, leaving me with milliliters. That's great news because I was asked to solve for volume. So we're going to multiply 0.971 times 725, hit equals, divided by 1.4, and I'm getting 502.84. Milliliter is the only thing that didn't cancel out, so that's my unit. All right, let's ask ourselves if that answer makes sense. So it looks like my volume went from 725 milliliters down to 502. So if the volume got smaller, that would only happen if the pressure got larger. And the pressure did go from 0.971 to 1.4. So the pressure went up, so it made sense that the volume went down. So that's how we handle Boyle's Law. You know that you have a Boyle's Law problem when you only have pressures and volumes to work with, and they either tell you that the temperature is constant, or they don't mention temperature, or maybe they give you an initial temperature and it doesn't change. The big thing is temperature stays the same the whole time. So the next video will actually be on Charles's Law, followed by Gay-Lussac, and then the combined gas law. This is the first of 4. We'll get through that series first, and then we'll work on the ideal gas law.